It's my pleasure to welcome Professor Sriram Sankaranarayanan. There we go.
Perfect.
Yeah. And who's an associate professor currently at University of Colorado Boulder. He got his PhD in 2005 at Stanford University and worked in industry for a couple of years before starting his current position. And he's won numerous awards. I won't list all of them, but some of them include the NSF Career Award and the Outstanding Teaching Award. And so a lot of his interests kind of revolve around automated reasoning for cyber-physical systems. And we'll be hearing today about that transition from his more theoretical work into the domain of medical devices and verification. Right. So please join me in welcoming our speaker.
Thank you. I must thank Eric for being such a nice host today. He's been nothing short of wonderful. And thanks to all of everyone who met with me and shared your work with me. It was great. Oh, no. That's par for the course, right? So I have to acknowledge some people. I might as well do at the start because I have a flight to catch immediately after this talk. So might as well thank some collaborators, mostly Greg Forlenza, University of Colorado Medical School, and David Maas, who's now at the Stanford University Medical School. A lot of this was also work with Faye Cameron and Georgios Finakos. All right. I don't have to introduce what a cyber-physical system is to this group. So you all know what a cyber-physical system is, and you all know why it is important. You all know why we need to verify this. Let me just move on and talk about automated insulin delivery. Why is this important? Why is this hard to verify? All right. So in automated insulin delivery, also called the artificial pancreas, the goal is to treat type 1 diabetes by infusing insulin externally. So insulin, what is insulin? Insulin is a hormone that is very important in regulating blood glucose levels. How is it important? It binds to some receptors in the cell that promotes the uptake of glucose by certain kinds of cells, including musculoskeletal cells. It encourages the liver not to break down glycogen into glucose. It encourages certain fat cells to take up glucose. So the main idea of insulin is it's a hormone that reduces blood glucose levels. So it achieves the control by reducing blood glucose levels. People with type 1 diabetes cannot make insulin because of an autoimmune response that destroys the beta cells, the islet cells in their pancreas. They are unable to make insulin, and therefore they need external insulin or external insulin-like analogs to regulate their blood glucose levels. And typically this is delivered using an insulin infusion pump. And the blood glucose levels are sensed by a sensor called a continuous glucose monitor, which goes under the skin and has a coated platinum thing that on which you have reactions. The reaction generates a current. The current generates a glucose signal that's calibrated and measured almost continuously over time. Right. So this is the overall control setup, very much like thermostat or very much like a cruise control. So what can go wrong? Right? Many things can go wrong. The first thing that can go wrong is the human body has a very, very low tolerance for low insulin, low glucose levels, right? So the normal blood glucose levels are between 70 mg per dl, milligrams per deciliter of blood, to 180 mg per dl, and that's called the normal glycemic range. Anything below 70 is called hypoglycemia. All right, and levels as low as 40 mg per dl can be very serious. Below that can be fatal. So it's very, very dangerous. And if you have too much insulin, that can end up depressing the blood glucose levels too much and can cause death in the patient. On the other hand, too little insulin means that the patient ends up in what I have colored like blue approximately there. And that's called hyperglycemia, about 180 mg per dl. That's not a short-term problem, but that's a long-term problem. So if it persists for a long time, the patient ends up having damage to their eyes, kidneys, nerve endings, so on and so forth. So their life expectancy is drastically shortened in the long term. So your controller has to keep your blood glucose level between two safe ranges. The problem, however, arises because your sensors are not very reliable. They are highly noisy. There is sensing delay because this depends on a biochemical reaction that happens under the skin. There is a lot of delay between changes in the underlying blood glucose levels and the sensor picking up those changes. The sensor can attenuate, so if the patient puts pressure on the sensor by lying down on the sensor or somehow changing the location of the sensor, it can actually, the signal can drop off, attenuate, and so on. So there are problems at the sensor side. And there are problems at the insulin side itself, right? So insulin cannot be delivered because your set may fail. Unfortunately, insulin being a hormone, it has, when it's infused, it has some time before which it starts acting, about 20 minutes or so. And then it has a persistence, which means that if you once infuse insulin, it stays in the body for about 7 hours. Before it's metabolized out. So there is a long persistence. So you can't take away insulin that you've already given and that may go on to cause hypoglycemia. So it's a very difficult control problem. It requires a lot of prediction out into the future if you want to control. All right, so that makes the control problem difficult and it's safety critical, and therefore you really need to make sure your controller is correct. So a lot of my research is on verification of cyber physical systems. I would like to build this ideal verification tool which takes in a closed loop model, a bunch of property specifications, environment specification, which is also important here. Crunch through all of that and then either come up with a proof of correctness or a counterexample. But the bane of my existence is this question mark in the middle, because often enough we are unable to resolve the property, the model with the environment specification, either to prove the property or falsify the property. We are stuck somewhere in the middle where we don't know, right? So that's usually where we are with these things. So with this background, let's look at what does it mean to verify the correctness of an insulin delivery system, right? So verification has to start from some kind of model. So it turns out, luckily for us, that there has been about 30 years of model building that takes in models of how insulin affects blood glucose levels in human patients. This started with work from Bergman in 1970s and continued on until the current day, where you have models like the Dalaman model and the Havorka model. These are large 10 to 15 state variable nonlinear models. They are differential equation models as well. So that part is great. So you can use those models off the shelf. And the good news is also that the FDA has approved the use of these mathematical models as a replacement for animal trials. So models can actually help us save animals from being hurt now, because you don't have to experiment on monkeys or dogs or guinea pigs. You can experiment on this mathematical model, which is great. And you can put these together in a model of the continuous glucose sensor with all the delays, the noise all added in there. You can have a model of your control algorithm and you can simulate this closed loop model. You can also specify your environment, and this is where it gets more complicated because the environment here is the behavior of the patient around the meals they do, around the exercise they do. And so you could say, let me have a normal behavior where I say the patient eats sometime between 6 to 8 p.m. They have what's called a pre-meal bolus they give themselves. They have a meal time. The amount of carbs in the meal can vary. The amount of insulin can vary. So you can specify a little bit of how the human behaves around this device. And together you want to have property specifications as well. So you want to say the blood glucose levels do not exceed 70 mg per dl. So do not, or stay below it. They should not exceed 300 mg per dl. They should not exceed 180 mg per dl continuously for more than 3 hours. If the blood glucose levels go below this, then insulin delivery must be stopped. So you can have a bunch of properties. We came up with a large number of these properties. And now the question is, how do you verify these things? So you have a large ODE model, you have a control algorithm, you have some non-deterministic environment specification and some temporal properties, and you want to either verify these properties or falsify these properties.
Advice for a property come out from the optimal control.
Which one? Sorry.
Maybe insulin delivery. Isn't that the actuation that you have in the control?
It depends. So it should, right? So if your controller is a regular, it's a controller like a PID controller with some, right? So or if your controller is based on MPC, it should come out. There are some control algorithms which are just like 180 lines of C code which have a bunch of rules. If this, then this. If that, then that, right? So one of the questions you can ask is, are there situations where the patient can actually go below 70 mg per DL, but some strange combination of circumstances means that the controller, the rule-based controller, actually delivers insulin for them, right? And we found that this is possible. In that controller we analyzed in a paper, we actually showed that there is a slip through which allows insulin to deliver under some strange circumstances to the patient, right? So yes, in a like regular control design scheme, like you use MPC, things are good. But when people use their rule-based control or something called a fuzzy logic control, it can fall through.
But the first three are real, right? Because this is the specification of what the controller should do.
Yes.
The fourth one is a trick to prevent some control algorithm to do the wrong thing.
Correct.
So I wouldn't put them together.
I agree. And so I have about 18 of them in which I actually classified, things as like things that should hold for the patient, things that should hold for the controller. Yes, in this slide they are together, but I did have them separate in our paper. Okay, good. All right. So verification approaches. So long ago we dreamt of a verification tool that could solve all verification problems where if the if the system actually satisfied the property, you spit out a proof. If the system actually violated a property, you spit out a counterexample, one tool to rule them all. But then I think over the years, we've kind of given up on this, and we've came up with building two types of tools, falsification tools and verification tools. Falsification tools are tools that are biased towards finding property violations. So they systematically test your system. You would say this is testing, it's automated testing, but I would say it's automated testing plus. You are doing some intelligent search for a counterexample and trying to make that search actually meaningful. And there are tools like S-Taliro, Breach, and a bunch of other tools that do this kind of counterexample search. Verification, on the other hand, is to show that no property violations can exist. And the reason I made this is verification presupposes that your property is true somehow, and you want to actually find a proof of the property, all right, as opposed to falsification. Idea is to explore all possible inputs. And depending on your setting, it's very hard to say, what are all the verification tools. There are different verification tools for discrete finite state systems, for hybrid systems, for continuous systems with differential equations. So I've tried to summarize a few well-known verification tools we use at least for hybrid systems with nonlinear differential equations, hybrid dynamics, and so on. And it's hardly exhaustive, and the list goes on, right? We just wanted to start doing this for falsification. So we have a falsification tool called S-Taliro, and the idea behind S-Taliro was to minimize quote unquote a fitness function defined over trajectories. And the fitness function is also called robustness. It's a measure of how close your system trajectory is to satisfying or violating a property, and you can use that closeness in an optimization loop to satisfy or violate the property. And I'm sure everyone knows about it, so I just skipped through all the S-Taliro slides and just mentioned that, okay, we have applications of S-Taliro to controllers from Toyota. We collaborated with them just like Sanjit did for many years. And so there is work on requirements mining, again, things that came out of Sanjit's group as well. And there are improvements to robustness metrics. So this is an active, ongoing field of research. I didn't want to go too deep into it. I'm sure everyone here has worked on it, knows a lot about it already, right? So let me just talk about the falsification of properties of artificial pancreas controllers. And our initial foray into this whole thing was to apply falsification to the controllers we had, right? So we started off that way. And so in the falsification setup, we replaced the patient by a differential equation model with about 11 state variables, about 30 patient parameters. This differential equation model is freely published. The 30 patient parameters are available for $500. So there is a way to get it from a tool which is sold commercially for $500. You can just read off the parameters if you hack into it. And there is a PID, discrete PID-based feedback law, which was published by all these people here. The importance of this PID-based law is it actually has a lot of anti-wind-up compensation and a little bit more to ensure that the delays in the actuation don't end up killing the patient. With all of that, it's actually very important because it's part of a commercially approved product now called Medtronic 670. So that product is actually out in the market and people are using it. So it's very, very important for us to verify how that device works, and nicely because it comes out of university research, we get access to all the control laws that have been used inside that. So we did this verification a while ago where we had this virtual clinical protocol. So in the virtual clinical protocol, we have our patient assume the patient's taking 2 meals. We have a time interval for each of the meals. We have an amount of carbohydrates within some range for each of the meals. And if you collect all of it together, the scenario has about 160 parameters. So varying these 160 parameters gives us a different form of the scenario, and we want to know, is there a setting of this 160 parameters that makes our system violate the property? So we boil everything down to a parameter search in a large dimensional space. So we set up our tool S-Taliro to do all of this. Again, the main idea here is S-Taliro just takes MATLAB code, so you can just use your MATLAB code. You simulate your MATLAB code, and the parameters basically affect how everything behaves. Question?
Are you using a brute force parameter search of lots of combinations, or are you
No.
studying methodologies?
So that's what, okay, so that's what we are not doing, right? So brute force search would be too much. What's happening here is we simulate the whole system, we get a trace, and out of that trace, based on the property, we compute a number called the robustness. If the robustness is negative, then the system violates the property. But if the robustness is positive, then the system satisfies the property. But the smaller it gets, the system is getting closer and closer. So we use a stochastic optimization like Monte Carlo optimization or a Bayesian optimization here to drive the testing so that it tamps down on the robustness. Hopefully the robustness goes negative, right? So it's not a blind search, it's more like a goal-directed search. Yeah. But unfortunately the robustness is a horrible, nasty function because you can't paper over undecidability that way, right? But it's still better than blind searching.
So in the end you get a parameter combination that is violating.
Exactly. You get a parameter combination that's a violation, yes.
What is the signal at the output of the Taliro, the robustness computation?
That's a number. It's just instead of saying whether your trace satisfies the property, it gives you a number. Like the trace is 0.5 robust with the property, or the trace is minus 0.2 robust with the property, right? So this whole thing is just a function. It just maps your system model input, the trace, to a number with respect to the property.
The distance between the solution and the boundary?
That's right, of the property. Yeah. And you define it for a safety property, it's just the distance between the trace, the closest the trace approaches to the property. But of more complicated temporal property, you can define it as a distance.
It could be like a simulation.
It's based on that, right? So there is a connection to being like closer to it. Yeah. It comes out of work from George Papas and Finacos and Antoine Girard. Yeah. So it's related to that, yes. But simulation metric is between two systems. Here it's between a trace and a property. So, I'm just describing old work because I'm trying to build up motivation for something we want to do, right? So we did falsification in S-Taliro using this model, using the parameters, using the properties, and we either find a violation or we find a least robust trace so far. As I said, we have about 18 properties across the 2 studies we did. But I can show you some of the properties here, so you can write those properties out in temporal logic, like metric temporal logic. And for example, for some of the properties, we don't find a violation, but we find like a near violation. So one example is, can we make the controller get the patient to a state where they are hypoglycemic? Turns out we can't violate it, but we come very close to it, about 75 mg per dl. And we can have these kinds of violations. For example, the controller is tuned so that it's very easy for the patient to go hyperglycemic, above the upper limit, right? So we did S-Taliro, and for some properties we found a violation, for some properties we found a near violation, for some properties we found no violation. So this was all meaningful, and yes?
Are you, in terms of generating the inputs, are you generating like the schedule of what the patient does as well?
Right. So for 2 meals, right? So we generate what the patient does for 2 meals, and then we simulate 12 hours out into the future. Yes. Yeah. So 2 meals and then 12 hours out. We are not repeating the meals, just 2 meals, and then the patient doesn't eat for. Yeah, it's like the nighttime simulation. So a meal and a snack, and then nothing else. Yes.
How are you simulating the variability and stochasticity of the patient's behavior?
So, excellent question. So that is where we got lost, right? Is there any stochasticity in the model? In the patient model itself, there is no stochasticity, right? So hold on to your question. That's exactly the question that bothered us, right? So I'll come to it in a second. Yes.
You have 30 patient parameters, 30 sets of patient parameters.
So each patient is described by 30 numbers.
Right. So when you say violate, that means you violated
one possible of those 30 numbers, because as you will see, how do we get those 30 numbers, right? So to us, this was maybe the end of a story, right? So we had, okay, ODE models are easy goods for simulation. You can always build an ODE model, put it in simulating state flow, simulate falsification, seem to work really well. But some properties are violated, key properties are not, and we tried it for a long time. I mean, I show you for 3.5 hours. We can run it for 24 hours. We still didn't get a violation, right? So is that enough, right? So that was the next question we wanted to ask, right? So we took existing models, we took our existing tools, we took existing clinical scenarios. By the way, those clinical scenarios were taken from the papers, the protocols they wrote for testing these devices for an outpatient clinical trial. So we got all of that correct, right? But the question is, what did we learn? And this bothered us a lot, because we could not show for real that key properties are not violated. Any violation we had, for example, the one case where we found a rule that slipped through and allowed insulin infusion, we reported it to the people who developed that controller, and they immediately changed their specification and turned their bug into a feature. Having done all of that, right, the question was, falsifications are falsifications, right? You show it to developers and they agree that these things can happen in real life. They may want to fix it. Sometimes they are like, because we didn't specify this properly, they made us change our properties, right? But something happens there. But if we didn't find any falsifications, what can we conclude, right? And unfortunately, we felt not much. So we wanted to go into verification of these things. So you could think about verification as just the flip of falsification. So now you have this environment specification, these properties, the models. Why not just prove it correct, right? Run a flow pipe computation for about 12 hours, like a reachability computation for 12 hours, it's like an overnight verification for a patient, right? Under all possible initial conditions. So maybe it should work out. There are a lot of verification approaches I can talk about, and I'm sure many of you know about it. The problem is we tried, and at least we tried our own tool called Flowstar on this problem, and it failed. After a bunch of hand-holding, after a bunch of slashing and simplifying the controller, it did succeed for a very stripped-down version of the controller where we handheld it along the way, and it did work. But that's not like going to please any of the clinicians, right? If you take them and change their controller, you're already doing something different, right? So turns out that it's really challenging to do verification for nonlinear ODE models and control software. So then we actually started questioning these ODE models, right? So who's this Dalaman and Kobeli? Well, they are very famous people, but we started figuring out like what exists in these models and why do we need a 11-state model with 40 patient parameters? What are they, right? And so we looked at how do these 40 patient parameters come about, right? And we found out that they are coming about because they are feeding these patients like radioactive labeled glucose, and tracer labeled glucose, and then they start studying how the tracer labeled glucose spreads through various parts of the body. They give them tracer labeled insulin, they measure blood insulin levels, they poke a needle and measure amount of glucose in the blood in the portal vein right close to the liver. All of this sounded super intrusive and we can't do that to patients, right? So these 40 patient parameters are identified on data that's really difficult to obtain, right? As such, the kind of data that we have is a noisy blood glucose reading, the amount of insulin that goes into the patient, and sometimes if we are lucky, we have some decent reporting of meals. Often we don't have any reporting of meals. People completely underestimate or sometimes overestimate how much they eat, so none of that is reliable. We have something about what they thought they ate, right? And when they thought they ate it. So, and then the variables in the model likewise are not meaningful variables for us. There is a variable on blood insulin concentration, very difficult to measure because its units are in nanograms per milliliter. There is a variable on glucose uptake by the central nervous system, which is, the reason it's there is because the central nervous system apparently doesn't need insulin to regulate its glucose uptake. Its glucose uptake is called insulin independent uptake. But how do we measure that in a real person, right? Sounds like really hard to measure how much glucose your brain is using at any time, or insulin dependent glucose uptake, which is everything else. Glycogenolysis rate in the liver, which is how fast is your liver breaking down glycogen, which is how it stores glucose in it. Insulin concentration in effect chamber, which is a mysterious like chamber that exists, which is not like a physiological chamber. It's just a variable added to the differential equation that says we'll add this to make it fit to the data, right? So it's not physiologically relevant. So should we need these kinds of physiologically relevant models? So they are really good for simulations. So therefore they are really good for falsification, but they don't correspond to any one person that we can point out to. Maybe they are population level models, right? And are they the best choice for verification when you actually want to prove something over a bunch of people? So we decided to drop this idea of using ODE models for verification and go towards non-deterministic models. So here we wanted to build these models where they are not going to attempt to predict blood glucose levels precisely, but they are going to attempt to predict an interval in which the blood glucose level may lie in the future. Okay, and the hope was that by building these simple non-deterministic models, we can maybe kill two stones at the same time. Maybe one, make these models simple enough that we can do verification. We can actually think about doing reachability analysis. They don't have to be this huge 10-state nonlinear 40 parameter monstrosity. Maybe they can be made smaller, simpler, even I dare say linear. So we could try that, right? Other thing is, from the point of view of verification, I feel like more non-determinism is always better. Because more non-determinism means that you are allowing more behaviors to go through by being less certain and being less pedantic about what the behavior should be. So we first tried this with a linear, it's called an ARMAX model, but that's just in quotes because it's not really that. So we just tried a linear model with uncertainty, and we got some very interesting results. And then we tried some what we call shallow neural network, tongue-in-cheek, because these are not deep neural network models of patients with type 1 diabetes. And again, we tried to do the uncertainty quantification for neural networks there. So one of the papers appears in ICCPS. Another paper, like the preliminary version, appeared in a conference called CMSP. It's under submission to a diabetes journal right now. So I'll quickly talk about these two papers and tell you what we did and what we learned from these two models, and at least give you an interesting modeling style to consider. So one of the key targets for modeling blood glucose levels, it's a time series. So you can think about how we could use time series models to forecast a future blood glucose level based on past blood glucose levels. So as an example, you have as an input to the model some k past blood glucose readings. So g of t, gt minus delta g to gt minus k delta g. So some past history. You also have some past history of insulin. Even though I wrote one term, it's actually a bunch of past insulin terms. All right. So what you want to do is use these to predict a future blood glucose level, gt plus delta g.
That input is insulin being applied.
Yes, it's the insulin being applied, but it's actually history of insulin being applied. I just didn't write the whole series there, but it's the insulin inputs and the glucose inputs. Yes.
How much history did you use, and how much time series data did you have?
Excellent. So I'll tell you, I'll answer both of that. But for one of the models, we used a very small amount of history. For the other model, we used a lot of history. But I'll give you the answer for each of them. All right? Yeah, we have patient data. So now we actually have data from clinical trials on about 30 patients. I'll explain what the data is about and so on. But we used the data, we took some of the data, held it out, used the other part of the data and validated it that way. We did a k-fold cross-validation. Okay. All right. So the main question here, these are very well-known models. These kinds of time series models are called ARMAX models. I usually get this wrong. It's auto-regressive moving average state space models. Okay. These are very, very standard in time series analysis, very well studied, and you can learn them using regression. Right? And the real thing here is this error term E of t, which is just the error, the residual from your regression. Right? So it's very easy to learn if you have data using regression. The usual thing people ask is what should delta sub g be, which is the time delay for the glucose, and what should p be, what should be the look back on this. And there are some criteria for this, like AIC, the Akaiki information criteria, or the Bayesian information criterion. So there are some heuristics that allow you to select this, but the bigger problem is it's a model selection problem. Okay, and the last question here is how do we capture the uncertainty in this model? All right. So what we did was to use something called a partial autocorrelation function, which is a standard way of figuring out what the delay should be and how much history we should be looking at. But the interesting thing we also did is rather than use a single model, we actually combine large number of models. So we combined 5 models, or each model accesses a different part of the historical data. So each model has a different P, it has a different delta sub G, it has a different delta sub I. And the main thing is the models no longer predict a point value, they predict an interval value. So we changed the models from predicting a definite point value of glucose to saying that the future glucose will lie inside an interval L comma U plus the core prediction of this model. So instead of making it a point valued model, we made it an interval valued model. And instead of choosing one interval valued model, we said, why not let's choose 5, right? Why not choose 10, right? So we just selected a bunch of interval models using this PACF criterion, like the top 1, 2, 3, 4, 5, right? And how does composing 5 interval model works? Very simple. Each model takes a different part of your history, like let's say a blue model, a green model, and a red model. Each takes a different part of your history and says your future blood glucose level lies in a different interval, and you just take the intersection of the intervals predicted by all the models as your interval. All right. How do you make these intervals? Well, this is what we did. We took the residual distribution of error and we took a confidence interval that corresponded to a 99% confidence interval. So each of those intervals has a 1% chance that you draw a blood glucose level outside that interval. Now, if you have 5 such models, that shrinks your confidence from 99% to 95%. Why is that? Because it's 5% chance through Boole's inequality that one of the models is wrong and therefore your intersection is wrong. Right? So you get, if you use 5 models, each model at 99%, you can conservatively say that the combined model has a 95% confidence interval for getting your right prediction. Okay, so that's how we decided on like choosing, let's say, 5 models and 95% confidence, right? Each model set at 99% confidence. All right. So we use a held out data set and then we tested the model. So just to reinforce, this is what our model predictions look like, these 2 red dotted lines, and the actual data looks like in the middle. And just to answer your question, we had data from about 50 patients from a clinical trial. Each patient, we had data for about 30 nights. It was just nighttime data. We didn't have, for this experiment, we didn't have daytime data. So we didn't bother with meals in our experiment. We didn't bother with exercise either, because generally people don't exercise in the nighttime. So we dropped meals and exercise, very convenient. But we could take nighttime data and build these interval valued models. All right. And now the problem with interval valued models is you can't simulate them, because they are giving you an interval and we don't associate a distribution with this interval. These intervals are just sets in which we know the future glucose level rise. There's no distribution. So there's no way of picking a point and then simulating further, right? So these are intervals, but you can use them for verification, because these intervals are just constraints. So the models are just providing us constraints on where can the future glucose levels be, and therefore if you use them in a constraint solver, you can use them for verification, for reachability analysis. All right, so the details are very simple. Once you realize you can use them as constraints, you can use a bounded model checking, or you can just unroll your models for some number of steps, and you get a big constraint system that you can use to generate all possible trajectories of glucose. Okay, and so what we did here was we put the PID controller in a closed loop with this data driven model and did reachability analysis. Okay, and because the data driven model needs an initial history to start up the model, before time 0 you need an initial history. We assume that the initial history is all possible normal glycemic ranges. So every possible glucose value between 70 to 180 was possible, and every possible reasonable quote unquote insulin level was possible. So we had a range and we said any possible insulin could have been given to the patient. The glucose level could have been any possible value between 70 to 180. So we had this set valued initial history, and we can now run a reachability analysis. How does that work? Well, you take your data driven model, write them as constraints. You take your PID controller equations, write them as constraints, and then you recursively feed the output insulin into the next data driven model, unroll it case steps, and now you have an optimization problem where you want to know what's the largest or the smallest blood glucose level that can be predicted at some point in time. So you have a maximization or a minimization problem. And because the PID control has saturation, you have to handle your saturation carefully. So it all encodes into a mixed integer optimization problem. Okay. Oh, it's a little more complicated. It's a good question. How is time encoded? Because each model takes in some past history and predicts glucose a little bit farther into the future. So you have to imagine these models are like tooth combed to each other. All right. So there is a unknown blood glucose value every 5 minutes down the line. And what you have to do is write constraints on how these blood glucose values relate to the past values according to the model. It's a little complicated. I wish I had a nice picture for it, but it's like a tooth comb because each model takes in some history, predicts some future. Yes?
Maybe a similar question. How do you pick the time horizon that you're going to predict over? Like, how do you pick how crossed over those tooth combs are?
We pick 5 minutes because the blood glucose levels are available to us every 5 minutes. So the tooth combs are all multiples of 5 minutes. Now the distance between the tooth comb was given by something called the partial autocorrelation function. And so we use that to select like 5 different models, each of which is a different multiple of 5 minutes. And it predicts out into the future. I think we predicted 30 minutes out into the future. So we kind of have like a bunch of tooth combs which kind of mesh along each other, and each of them tries to predict for a particular time. And you know you have to unroll the model. When you do that, you basically get a big mixed integer optimization problem, and we use that to minimize or find the minimum or maximum blood glucose level at any time, and that's basically reachability analysis for us. Okay. So we did this for various patients. So for example, here is one patient for which we found that the blood glucose levels are settling really nicely inside the 80 to 120 mg per dl range for this patient. Here is another patient for whom the blood glucose levels are really not settling. So if you find at 300 minutes, the blood glucose levels are basically all over the place. And so we found that, of course, like any PID controller, this controller depends on 6 different parameters. And they are all tuned according to a rule of thumb. The rule of thumb is to take the patient's daily insulin requirement, which is a number that every patient has, divide that by 1300, set that to your KP, your proportional gain. Integral gain is divide that by 120, that's your integral gain. Multiply that by 2.5, that's your. So you can see how these gains are all set from one patient parameter. So they have a rule of thumb for tuning that. Interestingly, for some patients, the rule of thumb seems to work really well. And for some patients, the rule of thumb fared really poorly. Now, of course, because we have a reachability analysis, we can take data for patients like this and convert it to data like this by changing the way the controller is being tuned. We can test different tuning parameters, do reachability analysis, and see if it's getting better, right? So we did that on the entire cohort of our patients. So this is how it looked initially. So this is through something called daily insulin units, the amount of daily insulin they need. And so this is our predicted blood glucose range for each of those patients. Now we have a lot of scenarios for each of these patients. So those are the small dots, but the big dots show like the prediction for each of them, the maximum and the minimum. And you can see a definite trend here. As the daily insulin requirements are going better, the controller as published seems to do much better. So what was the explanation here? Well, this was their. No, it's actually this way around for a good reason, because the clinical exclusion criterion was this. So this was the exclusion criterion for clinical trials. The patients who participated in the clinical trial were all here. These were the patients who were excluded from the clinical trials. So because patients who are poorly controlled need a lot more insulin, those were the patients who were put under clinical trials to see whether they could get a bigger improvement from the controller. And because the clinical trials were not choosing these patients who were already very well controlled, and if their daily insulin requirements is less, it also means that they might have some ability to secrete insulin in their bodies already. So those patients were excluded. Because they were excluded, the controller performs very poorly on them. Whereas the patients who are very low insulin secretion and who need a lot of insulin were included. So the controller, as it is, seems to do very well. So this is a result we actually confirmed with our clinical colleagues, and it is true that when the device hit the market, this is a published fact that people with lower daily insulin units did have a problem getting their blood glucose levels under control. So we had to find some match with existing data that could agree on what we were finding, right? So that was nice. The nice thing is we actually managed to retune the controllers and improve the performance for the patient. Yes?
Did you retune the controllers based on the reachability analysis?
Yes, based on the reachability analysis, we searched for 3 different parameters, KP, KD, and KI, the 3. Oh, we just had a discrete grid, so we know like minimum and maximum parameters. So we just selected like some number, like some thousands, and just we ran each of them and just chose the best in terms of hypoglycemia and hyperglycemia. Right? So it was a very easy. We didn't like do a continuous optimization. We just did a discrete grid search.
So you used the reach set to then inform how you chose the gains for the.
That's right.
Is that right?
That's right.
So you're using it as a tool for design.
Well, we are now using it as a tool for design because we are using it as a tool for changing these 3 gates, right? Yes.
Were the parameters fixed for all like across all controllers and all patients, or is parameters still based on like the daily requirements?
Yeah. So these were based on daily requirements. These were tuned by our search.
But is it the same controller for every single patient?
No. Different controllers, and we had a new rule. So we published a new rule that maps their daily insulin requirements to the new parameters that you should choose. So just like the old rule divided by 1300, we had a new rule that It's slightly more complicated rule, but we had a rule that said if it's above, if your daily insulin levels above this, do it this way. If it's below this, do it this way.
So
But
it still uses that one parameter, but just breaks it down in a more.
that's right. More bins based on the different patient groups we found. Right. So
But do you have access to this parameter in the actual device?
we do. I mean, that's a big story. We do. And if you change the parameter in the device, it actually will change it. Interestingly enough, it also overwrites your changes at every night and then just does its own thing. So unfortunately, we do and we don't. So I mean, so Medtronic will not acknowledge that their controller has anything to do with this and all that. But talking to them, they found it interesting. I gave the same talk at Medtronic just 2 weeks ago, and they found it really interesting we could do this. But now they have moved to their own adaptive thingy that they are not telling us. But it's scary, right? So it's very scary. I don't know what they are doing, but I would like to. If I knew what they were doing, I could verify it, right? So with these models, we could actually tell something about what it will do to real patients, which is very nice. One of the
Did you try to see the difference in the models, like the 40 parameters?
No, we didn't compare this to the Dalla-Mann model, frankly. I mean, so we could have, but that's something we haven't done it, right? We can try to do the same thing for the ODE models. The problem with these 40 parameter model is we can't fit those 40 parameters to any of the patient data we have. It's a very large nonlinear optimization problem. So we get local minima, and when we try the local minima, it works for a little bit of time, and then the model and the parameter, the data just deviate from each other.
Because it would be nice to say, well, this is a standard industry with parameters that are very different to measure this our the approach.
Yeah, no, that would be interesting, but right now we didn't even try to fit those Dalla-Mann model parameters to the data. I mean, we could. We did once, but it didn't work very well, so we gave up on it, right? So, okay. I have 10 more minutes. So, the next part, because we cannot handle daytime data, and because, we wanted predictions for a longer time horizon, we went and looked into how can we use neural networks for doing this prediction. And the idea here is exactly the same. You have a blood glucose history, and now we just use the whole 180 minutes of that history. We have an insulin history. We use 180 minutes because 180 minutes is past the peak action time of insulin. So this insulin that was given 3 hours ago would have been past the peak of its action. So it's useful to cut off insulin 3 hours in the past. So based on that, we want a blood glucose level, let's say 3 hours into the future. Right? So that was the overall prediction tasks we had for ourselves. So you all know what a neural network is. These circles actually represent different activation functions like sigmoid, hyotanH, ReLU, and so on. We just use a standard feed-forward neural network, nothing else, right? So interestingly enough, there has been a lot of work applying neural networks to blood glucose prediction. There was even an ICML blood glucose prediction competition last year using neural networks. But what we really found is that we didn't want to do deep neural networks because we want to use this in verification, and we wanted to try using this in control. So deep neural networks defeat our purpose. So what we wanted to do was the smallest, simplest neural network we can get away with. So the idea here is we tried to mimic, quote unquote, this is all a little bit of rocket science here. We tried to mimic how the physiology of insulin and glucose works. So we had an insulin only layer here, we had a glucose only layer here, and then we had a joint insulin glucose layer and an output. So that was the simple dumb thing that we tried to see if it could make things better, because we thought maybe we should make the network mimic the action curve of insulin, right? And then maybe it can learn that. It would be so cool if this layer actually learned that, and then maybe the whole thing just is nice, right? So that was just a vague intuition, right? How best to explain it. But to our surprise, we found that something like 2 layers with 8 neurons per layer gave us the best root mean squared error, which was unbelievably interesting. That very, very simple tiny network actually does much better for a 180-minute prediction than a much deeper network for a 60-minute prediction. So we have no way to explain that. But we found really small networks are really good at this without necessarily going into large networks or deep networks. We have about 30 patients, 60 nights per patient. For this study, we still have that. Yeah. 30 patients, about 30 nights per patient, that's all. So not even 60. Yeah, so, and then glucose data every 5 minutes for those 60, for those 30 patients, 30 nights, right? In any case, we didn't want, just like before, we didn't want our model to forecast a single value. We wanted our model to forecast an interval or at least a confidence interval, right? The way we did it is instead of training to minimize the L2 norm, which we also did, we also trained to minimize for the lower quantile and upper quantile. So this is a standard approach in statistics where you can use something called quantile regression. So in quantile regression, if you want to regress to the quantile of your distribution, like the 50th percentile would be the median, but the 80th percentile would be the upper quantile, the 20th percentile would be the lower 20th quantile. There is a systematic way to do it, and you do it by changing the loss function. So if you use this piecewise linear loss function, where the slope is 1 divided by 5 and 5, or 5 and 1 divided by 5, you are actually regressing to the quantile of your data, right? You need a lot of data for this, but we assumed we had enough data. So that's the part we didn't really verify. So we finally have something about the patient data that we used. So we used about 17 of the 30 patients we had, and we compared the study with the UVA Padova simulator, which is the Dalla-Mann model, and where we had about data for about 6 patients. So 6 parameter sets, each parameter set has about 30 parameters. So here's the interesting thing. So we did 2 quantile predictions. So this is I think a 20th percentile, and this is the 80th percentile in red, 20th percentile in blue. So for the real data, you see it's like somewhat messy. For the synthetic data, you see a beautiful separation between the 2 quantiles, which is often the case, right? But we had lower quantile predictions and upper quantile predictions. So we have a network that can predict something that's consistently a lower bound, consistently an upper bound. We verified the prediction accuracy, and we have improved this predictive model a lot in collaboration with people at University of Virginia. So there they have a data set with 24 people that includes daytime data and includes much longer period of observation, about 90 days or more per patient. So and we had a much nicer root mean squared error. So for example, we can predict about 4 hours out into the future with an error of about 40 mg per dl. And then for about 120 minutes, we can have about 38 mg per dl. This Clark error grid is a different kind of analysis which talks about how often do we predict hypoglycemia when the patient is not under hypoglycemia. So it's a risk-based scale. I don't want to explain it, but those numbers look good as well. So the interesting thing here is we are using this for a MPC scheme. So you can use a mixed integer linear program to now compute control for if you have neural networks, and our neural networks are small enough that we could actually use an MPC controller with the neural networks. And so we are also looking into parameter tuning for PID. So this is just work that's coming out where we are comparing this way of doing it with neural networks with our previous way of doing it with the linear models, and we want to make sure that we get the same answer from both comparisons. That's the only way I think you can get confidence. If you try different data-driven approaches and you get the same answer, maybe it's something real about the data, and maybe it's not something that you're imagining, or it's not an artifact. So in terms of future directions, the first thing we noticed is neural networks are really dangerous if you just predict blood glucose levels. Why is that? So if you notice in our data, we didn't have meals, so no one reports meals. We just have insulin and we have blood glucose levels. But every time patient gives themselves insulin, they are also eating a meal. People correlate meals with insulin. So But the problem is after they have an insulin, their blood glucose level goes up. So the neural network has no way of knowing that it's the insulin, it's the meal that's causing the blood glucose levels to go up. It figures that the insulin causes blood glucose levels to go up. So even though the accuracies are great, it has just learned the wrong biological fact that insulin is positively correlated with blood glucose, whereas insulin is actually negatively correlated. Right? So the wrong correlation in the data is causing the model to learn a wrong causality, which if you use it, it will be very accurate, but if you're using it outside a meal situation, it will kill the patient. Right? So this is dangerous, right? So then how can we hard code the negative dependence of insulin in the data? Right? So insulin has to negatively affect blood glucose levels. So we need to learn a model that hard codes it. So that's important. Another really important fact is we have to have better models of how humans interact with these devices. So as an example, there is a classification of human interactions like abuse, misuse, and disuse. Abuse talks about overutilization of autonomy. Misuse talks about underutilization, and disuse, for example, is like an off-label use of automation which can endanger the person. As an example, people are misusing the Medtronic 670G device by reporting the wrong daily insulin requirement, giving it the wrong sensor values just to make sure that it gives them more insulin than and break the automatic like safeguards in the device because people want more insulin and they think the device gives them too little insulin. They are working around the automation. We are also working on something called runtime predictive monitoring, where we are really interested in using these models in real time to predict impending hypoglycemia well before the fact. So that's all I had to say today. Thank you so much, and I'll take any questions.